Dear friends, ladies and gentlemen, in this speech devoted to the memory of Professor Van Bledel, I would like to draw your attention to his power of intuition, supported also by his large and deep knowledge of mathematics and physics. To this end, I reconsider the double current sheet problem considered some 30 years ago by himself and compare his results with those obtained by the distribution concept. In order to be able to interpret correctly his results and to clarify the mathematical operations made by intuition to arrive them, we have to remember something about the concept of the generalized functions in the sense of distribution. As is well known, an appealing property of the distribution concept is that without any restriction, they have derivatives of all orders. For example, for a vector-valued bounded and piecewise differentiable function E, which has discontinuities on a regular surface S, which moves arbitrarily, one has to curl divergence and the time derivative in these forms. Here we assume that in an orthogonal coordinate system UVW, the surface S is determined by W equals 0 and N is the arbitrarily oriented unit normal vector to S, while V stands for the velocity of the surface S. Delta W taking place in these equations is the usual Dirac distribution. As to the quantities denoted by the curved brackets, they stand for the expressions outside S, which consist of continuously differentiable functions. They are called the regular parts of the corresponding quantities. The quantities denoted by the double brackets denoted the increments to be observed when one crosses S in the normal direction. The terms which involve delta W are called the singular parts of the corresponding quantities. Apparition of the distribution concept had naturally caused to the question, are the already known differential equations of the theoretical physics valid in the four-dimensional space in the sense of distribution? It goes without saying that the answer to this question is not naturally and imperatively affirmative, because the generalization made in the sense of distribution was in a rather particular direction chosen by Lawrence Schwartz. For example, the multiplication of this kind of two generalized functions is not definite, which excludes the nonlinear equations such as the Navier-Stokes equations of the fluid mechanics. Therefore, an affirmative answer of the aforementioned question is an additional postulate put on the equations in question. Assumption of this postulate for the Maxwell equations in a non-homogeneous space yields very important and interesting issues. Now, I would like to remind some of them very briefly. Consider, for example, the Maxwell equations and assume that they are valid in the sense of distribution in a space divided into parts as shown in this figure. Since some components of the field exhibit jump-type discontinuities on S, the field components have expressions of this form. The coefficients E sub 0, E sub 1, etc. are all functions defined on S, while M appearing on the last term is the order of the field. Similar expressions are also valid for the densities of the source. If we insert this kind of expressions into the Maxwell equations and equate the terms of the same order taking place in the left and right-hand sides, then we observe that the regular parts are reduced to the already known relations, valid inside the simple domain separated by S, while the coefficients of delta KW yield these equations. Now consider the case when S consists of a sheet which carries only dipoles and current of dipoles in the empty space. In this case, the charge densities are as indicated here. From the compatibility conditions, one gets E sub 0 and H sub 0. They are the singular parts of the field concentrated on the moving discontinuity surface. If one inserts these expressions into the boundary conditions, one obtains the boundary relations satisfied on a moving double sheet. Now assume that the sheet is at rest and the current is time harmonic, while the coordinate system is such that lambda equal to 1. Then one gets this more simple expressions. It is interesting to notice here that without recourse to the aforementioned distribution postulate, von Bleder had obtained quite correctly the results written in green through an intuitive approach. But his approach could not permit him to find the relations written in yellow. Now I would like to present the essential points of his interesting approach. Professor van Bredel had considered the double current sheet as the limit case of the layer depicted in the figure for H tending to 0. The result was obviously the sheet shown in the second figure. This is equivalent to our particular case considered just before. The starting point was this curved equation written explicitly in the previously mentioned coordinate system. It tacitly admitted that the system is such that the metric coefficients are H1, H2, and 1. The assumption H3 is equal to 1 yields lambda equal 1, which means that his case is equivalent to our previously considered particular case. The existence of the Dirac functions hints that these equations are valid for the limiting case obtained for H tending to 0. In this case, the space involves only points with W positive, W negative, and W equal to 0. In other words, there is no layer. But from time to time, he also says from these equations, it may be deduced that H tangent and E3 become infinite in the layer, and integrating out the depth of the sheet, etc. This kind of expressions seem at first glance to be meaningless. They hint that the reasoning of Professor van Bledel oscillates between the double sheet and the layer. Hence, his approach needs some elucidation. Now I will try to this end. To elucidate his intuition and to legitimate mathematical operations, I consider some small changes. H is not 0, but very small as compared to the wavelength. The coordinate surface W equals 0 is located in the midst of the layer. The function delta W is replaced by a continuous function delta WH, which tends to delta W when H tends to 0. For example, delta WH may be this exponential functions written in yellow. Thus, his original equations become as written here. By intuition, he claims that when H tends to 0, both H tangent and E3 grow infinitely. Thus, he equates the last terms in the left-hand sides of the first two equations to the last terms taking place in the right-hand sides, which yields the tangential component of the magnetic field as shown here. Then, by using it in the third equation, he gets the expression of the normal component of the electric field. Now, I would like to make a remark. To arrive at this result, he ignored the other terms indicated by blue arrows, which also go to infinity when H tends to 0. This is very important. If he had not made this ignorance and written his original equations like this, then he could not get the exact expressions. Although he did not explain the reason for his errors, I think he intuitively admitted that when H tends to 0, the magnetic field becomes of the same order as delta W, while its normal derivative is of order of delta prime W, and the latter is much more singular than the first. This difference in the orders of the singularities is obviously seen from the expression of delta WH. To get the boundary relations, he considered the other curl equation. In the first two of these equations, he replaces H1, H2, and E3 by their previously obtained asymptotic expressions and gets the normal derivatives of the tangential components of the electric field. These expressions are all valid inside the layer. Integration of them in the layer give the boundary conditions for the tangential component of the electric field. To obtain the relation connected to the normal component of the magnetic field, he considers the normal derivative of the third component of the curl equation and integrates it in the layer. Now, concluding my speech, I would like to say also something about the missing boundary conditions written in yellow. The asymptotic method used by Professor van Bladel did not permit him to find them. His attitude concerning these conditions, I guess, was determined by his intuitive claims stated as H tangent and E3 become infinite in the layer. And these components are continuous on both sides of the double sheet. The tangential E, on the other hand, suffers a jump. Thus, the left-hand sides of these relations may have seemed meaningless to him because they give rise to indeterminate forms such as infinite minus infinite. But as the right-hand sides show, these indeterminate forms have well-defined finite values which are usually non-zero on curved surfaces when the metric coefficients H1 and H2 depend also on the W coordinate. We'll always remember Professor van Bladel with admiration. I thank you very much for your kind interest.